Okay, now in this we are discussing the Maxwell's equations. We know what Maxwell's equations are. You had, for example, a question in the quiz. It was write down what are the postulates of the electrostatics and what were the postulates of magnetostatics. So the postulates, they have to do both with divergence and the curl of two fields. Okay. So this is what the postulates are about. And then the postulates of the magnetostatics, it would be the divergence of B and the curl of B. So this is how the postulates looks like from both, for the first field, which is the electric field, and for the second one, which is the magnetic field. Now, in a similar manner, these four equations that we see here, they constitute the four Maxwell's equation, but the Maxwell's equation, they are now sets of equations which are include also the time dependence. Okay, so this is something extra regarding the Maxwell's equation, because at this domain, the fields, they will be coupled, which means that the electric field will be strongly coupled to the magnetic field and vice versa. So a change in the respective fluxes, for example here, we would expect minus delta B over delta T. The curl, actually, let's write here the intensity. This would be equal to the rate of change of the flux. So we know that E and H, they are intensities, B and D, they are fluxes. B is equal to mu0 H, D is equal to EE. And then this is what we get. So at this, the curl of H, which is equal to this equation, this would be equal to the permittivity it gets out, derivative of the electric field intensity with respect to time. And then, if we use the Phasor notations, this would be equal to J omega times permittivity times the electric field, okay? Because at this, and similarly, for this equation here, we can erase this one for a moment, but before erasing, I need an eraser. So we can write this again, but if we continue on this side, this would be equal to the minus sign. It is only when we calculate the rate of change of the magnetic flux, and this would be equal to minus J omega permeability times H. So from here, just a small reminder, the rate of change of some quantity as a function of time, this will be equivalent to J omega. And we consider this one because we expect that the relevant fields to be equal to, wait a second, what is this? We have some orientation vector AN times E0 times e to the power j kr, okay, times e to the power j omega t. So the time derivative will produce a j omega. Now this kr, it is very important relation, because, not relation, it just shows how it is going to propagate in space, and the r vector. So how can we determine some point in space? Some point in space, which is x, y, z. We use the unit vectors, which denote. Sorry, this is az, which denote the directions for x, y, and z. In some textbooks, just to refresh your memory, you can also see them as I, j, k. And any point P in a three-dimensional space, how would you call those? How do we determine a point P? We call, in a general sense, we say x, y, z, right? So these are generalization of this point P. Similarly, any point R in space, we can denote this one as x, ax, plus y, ay, plus z, az, okay? So at this point, if we have here k dot r, then k dot r, it will be And let's assume that k, so this was the position vector, right? So any good student should remind that the position vector, this is how it looks like, because the general point found at the distance r, it can have coordinates x, y, z. This part is good, but then at the same time, let's assume that some electric field, it is propagating, and this is the propagation vector k. This will be equal to, let's say this is propagating along the AZ, right? So this vector will have some magnitude k moving along the kz, and then at this point we just say that k dot r will be equal to k dot az, all this dot product with x a x plus y ay plus z az. So we know that the dot product between az and ax, it will be 0. The dot product between az and ay will also be equal to 0. And then here we will simply get kz, right? That's why often in the equations of the electromagnetic waves, which are represented by a mathematical construct, which looks like this, we're going to see expressions like an, then ae0, the amplitude, e to the power j kz plus omega t. Okay, so this is, sorry, this became a little meshed up, but let me write this one here more clear. This is going to be e0 times the direction of the electric field, e to the power j kz plus omega t. Now, we have a convention, and this convention, we're going to use it because often when the material or the medium where the wave is propagating, if that one is conductive or it has some non-zero conductivity sigma, then in that case we might see some unexpected behavior, and this unexpected behavior actually once we come to that point, it would correspond to strengthening of the electric field in case the electric field, it should be attenuated. For that reason, just at this stage, it will become clear very soon, we do consider a convention that when an electromagnetic wave, if this one is moving along, let me do it like this. So let's say this is y, this is x. If the wave is moving along the positive x-axis, so if this is moving in this way, the E, it will be E0 minus jkx, okay? This is if the wave is traveling in the positive x direction. If the wave is traveling in the negative x direction, the field is e to the power jkx with a plus. But one thing that is worth noticing is that this is not the electric field, okay? So this is k. This vector k is equal to kax, okay? And here k is equal to k minus ax. Okay, so this is the direction of the k. The electric field, it is rather denoted as perpendicular, so this is electric field, okay? So in this case, if electric field is pointing along the AY, we just multiply here AY. And here we can also denote this one as AY. So we should not get confused with the direction of the electric field and the direction of the propagation. Actually, the representation of the electromagnetic waves, it rather looks like this. It is often represented by a photon, okay? And this photon, it has the propagation, this is the propagation K, this would be the electric field, and here we expect the magnetic field intensity H. And the orientation, or the relative orientation between the K vector, the E, and the H, it does preserve, or it does satisfy the right-hand rule, which means that the curl of K with E is going to be equal to the H, okay? And this approach we have used also in the previous session, or in the previous week, where we covered a couple of examples with the fields that can be given Just give me 1 second. So this is how we represent these waves. Okay. Yeah, there is a couple of examples here in the book. We can also look at these later. There is also, it's worth mentioning this one, there is also a very good or important relationship between the electric field intensity and the magnetic field intensity. Maybe we can also conclude it, not conclude, but okay. Okay, let's assume we have some magnetic field intensity, which can be written as follows. This is a function of x and time, and this is oriented along the z-axis with an amplitude of h0 cosine omega t minus beta x plus theta. Okay, so this is how the magnetic field intensity looks like, and this expression that you see here, we call this one the instantaneous expression. The instantaneous expression, this means that it is a function of time, because, so we call this one so if this is the instantaneous expression, it does depend on time, and we can clearly notice this here. This does represent the wave. Now, one question could be the following. So, what is the phasor? So find the phasor notation. To find the phasor notation, we know what we need to do. We need to remove the time dependence. And the time dependence, it is hidden in this term of omega t, based on the fact that it is relatively difficult to write cosine omega t minus beta x. It is relatively difficult to separate this one into terms as a function of cosine omega t and cosine beta x, right? So these are two functions. Since it is very difficult to do this, what we rather do is the following. We can write this one, e to the power j omega t minus beta x plus theta. And this whole thing, it can be written as follows. We can write this one, e to the power j omega t times e to the power minus j beta x e to the power j theta, right? So this is how we can represent this one. And now it is relatively easy to strip out the time dependence, or to strip it off, and to get the expression which is removing the time dependence. So this is the only thing we want to take away. In this case, this new expression of the h, but now this is a function of x alone. Okay, Phasor variegar pola. Okay, Phasor variegar absira. So this vector h is equal to az h0. Now I'm going to ask a couple of questions, so get ready. E to the power minus j beta x minus theta. Okay, so find the phasor. This is it. Now the first question is, what is the direction of propagation? Who can answer this? First of all, can you hear me? Can somebody confirm verbally? I will hear you. Johnny? Yes, okay, you wrote it down there. So my first question, you can also answer by writing in the chat session. What is the direction of propagation? What is the direction of the propagation? In which direction is the wave propagating? Let me check if you answer this one in the comment section. So what is the direction of propagation? Ce dreptime pe exemplarea? Livia? Can you answer this, Livia? O să te din? Let me have a look. Who else we have here? Oh, Andrew. Can you answer this, Andrew? Andrew Dimane? So what is the direction of the propagation of the wave? Now, the wave, it depends on x because it is moving toward the x. Okay, so that's why if h is a function of x, that means that the direction of the propagation is going to be along the x. So let's call it, and what does direction of propagation mean? Direction of propagation, it is in fact equivalent to k. What is k? That's what you're asking. K, it is k times ax, right? Let me check present. Okay, you wrote a couple of good comments down there. So this is ax. The question is, is it plus x or minus x? This one, it will be plus ax. So the wave, it is moving toward the positive values of x. The other question is, what is the polarization? Now this polarization, this is equivalent to the direction of the electric field. By convention, that's how we call it. We said that the polarization, it is defined by the direction of the electric field component, which means that this is equal to E0 times what orientation? Where is the electric field pointing? What can you say about this? Now, we said that the propagation of a wave, actually we still have this one here. So this would be the magnetic field intensity. So we have the right-hand rule, K dot E, we get H. So here, so let's see, here we have K, E, H. Clockwise, we give each other with a positive sign. Now, we want to find, so we found what is K, right? We know K, okay. What is H? H is given as h times az. This is h times az. So the direction of the electric field, it should be equal to, so whatever the direction of the electric field is, it should be h cross k. So let's see, what is h? It is az cross product with what was k, k was ax plus ax. So if we watch here, this is az cross ax, we have a clockwise rotation, so we get ax. So apparently, sorry, what is ay, sorry, this is ay plus ay. So this is the direction of the polarization of the wave, because this is what we are going to get. That's good. So far we've done polarization, propagation, direction, and so on. The next question is, let's assume that we have a wave which is, let's say we have a frequency which is 100 megahertz. Okay, so this is a wave which is 100 megahertz. And now we want to determine all the relevant parameters. So what would be the relevant parameters? First of all, we may want to figure out what is this omega. What is this radian per second, which is going to change the wave. Omega will be equal to 2 pi f. 2 pi f multiplied by this frequency, so this is going to be 200 pi, or we can write this one 2 pi, and by the way, this frequency is also equal to 10 to the power 8 hertz. Okay, then this omega, it is equal to 2 pi, 10 to the power 8, is it true? Yes. So this is omega. Then we have to look for beta. What is beta? This beta, or the propagation vector, in fact, apologies for a moment, we can also write this one k. The beta, it will be a generalization of the beta is equal to k. Both propagation vectors, the beta is more generalized because it's going to include also the cases when the waves move in a certain material, which can be magnetic, non-magnetic, etc. So beta is equal to k, this is equal to 2 pi over lambda. So what is the wavelength that our wave has? The wavelength, we don't know lambda yet. Wavelength is equal to lambda, it's equal to the speed of light divided by the frequency. So this is the wavelength. The speed of light is equal to 3 times 10 to the power 8 meter per second, divided by frequency, which is 10 to the power 8. And this is equal to 3 meters, okay? So this is lambda, this is equal to 3 meters, and we have 2 pi over lambda. This is equal to 2 pi divided by 3. This is beta, and the unit of this beta, it is a phase angle. So, wait a second, this is radian per meter. This is the unit of beta. And yeah. Okay, the next question is what is E? So what is E? In order to find E, we can have a look at this equation. We know that the curl of H, it is equal to the rate of change of the magnetic field intensity as a function of time. This is Maxwell's equation, okay? It starts from here. And then D, we write D as permittivity times E divided by time. Then E, it is a constant. We can take out of the derivative, but the derivative with respect to time, it is also equal to j omega if we write the Phasor notation. Now, here this is the Phasor notation, and now what should we do? We should calculate the curl of H. How do we calculate the curl of H? We say here AX, AY, AZ. And here we have a derivative with respect to X, derivative with respect to Y, derivative with respect to Z. H itself, it is 0, 0, and then here we have H0, the amplitude, times e to the power minus sorry, this is e to the power minus j beta x minus theta. Okay, so this is the curl. So this is equal to the curl of h. And this is then equal. So let's move fast. First of all, to find this one, we're going to expect here what is AX. By the way, in here, when we were trying to determine what was the polarization of the electric field, when we're trying to find the polarization of the electric field, we expected the orientation to be AY. Now we can also reconfirm this one when you see this expression. But so AX presumably is going to be equal to 0. Check this please. Minus AY. Now this should not be equal to 0. And how are we going to find that AY? This is going to be equal to the derivative with respect to x of this term minus the derivative with respect to z of this term. The derivative with respect to z of the 0, this is definitely right away 0, so let's leave it alone. And here we have AY times, let's write this one, derivative with respect to x of e to the power minus j beta x e to the power minus theta. And this derivative here, it is simply equal to minus j beta. Now, minus j beta plus j beta is going to be equal to, well, minus minus, it will be plus. So this whole curve, this will be equal to AY, let's write it here. This will be equal to AY times j beta h0 e to the power minus j beta x e to the power minus j theta, sorry, the j is still there. Okay, then this whole thing, let's not forget, this was equal to the curl of h, but this is also equal to j permittivity omega e. Okay, so because this is the other side of the equation. So when we see this equality, we can say that we can determine what is the electric field from this expression. So we would have to divide both sides by j, so we can cancel this out. So here, the electric field, here, it will be equal to, the j's are cancelled out. First of all, we can write down the orientation. It is AY, and then this will be equal to beta times H0 divided by omega times permittivity. Okay, what else? Please don't let us forget anything. And the phase notation, this is minus j beta x e to the power minus j theta. I believe I might have written something wrong. Let's have a look. Yes. There's a small mistake, not a big one. So this minus j theta, we can put here a plus. And okay, so we found the electric field. But now, one interesting aspect is that how is the relationship between the what's the name? What is the relationship between the amplitude of the E with H0? So if we see here, this is the amplitude of the electric field. So this one can also be written as HAY times the magnitude of the electric field, which is this whole piece of terms here, times the phasor, the exponential terms, which are written like this, minus j beta x minus theta. Okay. So here I just put this one inside, but you can follow what we are doing. And now let's have a look here. How these amplitudes between the electric field and the magnetic field are related. We see here that the E, it is equal to beta H0 divided by omega times permittivity. And we can also write, not this way, let's do it like this, E divided by h. This is going to be equal to beta, like this. Now, what is beta? Let's try to reformulate a few terms. Beta is equal to 2 pi over lambda. Okay? This is equal to 2 pi over lambda. But actually, we know what this is. Beta equals 2 pi over 3. And let's try this one. Beta, it is 2 pi over 3. What is omega? Omega, let me think for a moment. Yeah, let's do it like this. So omega, it is equal to 2 pi. And how much on the board? You can see this part. Okay, this is beta. 1 over omega, it will be, so 1 over omega, it will be like this. 2 pi times 10 to the power 8. This is 1 over omega. We have also 1 divided by the permittivity. What is the permittivity of free space? Permittivity of free space is 1 over, so this permittivity is this has a value like this, 8.85 times 10 to the power minus 12. It's a relatively small number. So here we divide by 8.25. And by the way, dividing by 10 to the power minus 12, it is the same way as multiplying by 10 to the power 12. So this is 10 to the power 12. I multiply it, and this is divided by 8.85. 8.85. So this is the ratio between the electric field intensity and the magnetic field intensity. Now here we can cancel here these 2 pi's. This would be equal to 10 to the power 12 divided by 10 to the power 8. This is equal to 10 to the power 4 divided by 3 times 8.85. And this one, this would be something around 120 pi. So this is for vacuum 120 pi, or equal also to the intrinsic impedance. Now, if this is carrying the word intrinsic impedance, we know that impedance it is something that impedes, but block on, it deteriorates, it diminishes, it weakens some field, and these components which do weaken, that do diminish the quality or the power or the intensity, we measure all of these with ohms, special resistance. It's a resistance the same way that the resistance of the unit of this one is this. Now, this looks like a little tricky. This is how we found this one. We could also have, so actually, personally, I don't like this one very much. I mean, it's not a choice, but personally, I like also, I cannot remember this one very easily, but I can remember this one much easier because mu0 is equal to 4 pi times 10 to the power minus 7. So I like this quantity more. Omega. So what you can look as an exercise, just try to look how is the omega related with the velocity. And how is this one related to the speed of light? We should look for the units actually. Omega is radian divided by second, right? Speed of light, this is equal to meter divided by second. So how can we get the units of the omega from the speed of light? I can wait for your answers, but it looks like we may have to multiply with radian per meter, right? So, because this is omega, this is the speed of light, meter per second, to get the units of this one, apparently we have to multiply with radian per meter, because meters will cancel out, and we will be good. Which quantity on the board has units of radian per meter? To me, it looks like they're right here. So that this will be done. This omega, it is equal to the speed of light times 2 pi over lambda, or times k, ck. Okay. So in this case, let's have a look at the board. Actually, I keep interchanging beta and k on the board. That means that when we move into more developed in the future chapters, you know precisely that they are almost the same thing, but it might be confusing to some degree actually. So, so beta is k anyway. So let's. So we have omega ck, anyway. ck, and this omega ck, this can also be written, omega can be written as k divided by the square root of something like this. And anyway, I can leave it here because you can do another change of the variables when you write over there the omega. And this also means that omega is equal to the 3 times 10 to the power times k. What was k? 2 pi over 3. 2 pi over 3, which is really what omega really was, okay? Okay, so it looks like this was the electric field given in here. And, yeah. Do you have any question? If there is no question, we can